Section: Introduction. In this section, we discuss how visual language, which combines text and images to convey information through charts, plots, and diagrams, poses challenges for multimodal reasoning. Connecting visual cues like color and positioning with textual elements such as legends and units is complex. While recent advancements in vision language models, VLMs, have enhanced the model's ability to grasp fundamental image components, the capability to perform intricate reasoning tasks by integrating image representation with textual understanding remains limited. Techniques like in-context learning and fine-tuning on datasets with rationales have been proposed to enhance reasoning in large language models, LLMs. Our work focuses on enhancing reasoning in VLMs by improving image representations and fine-tuning on synthetic datasets with reasoning traces. We also explore a hybrid online setup for refining numerical reasoning. Through experiments on ChartQA, a visual question answering task, we demonstrate that our approach boosts performance by enabling VLMs to reason effectively using complex visual information. VLMs like PolyX and Poly3 employ a hybrid architecture combining vision and language components to solve visual tasks. Training typically involves pre-training to learn a robust internal representation, followed by fine-tuning. However, Poly3 lags behind PolyX on ChartQA due to its limited reasoning abilities. Our findings suggest that the absence of a pre-training task for improving chart representations may contribute to this performance gap. Enhancing reasoning in large language models such as PaLM2 or GPT-4 is an active research area. While scaling up models aids in better knowledge retention, it does not necessarily enhance complex reasoning abilities. Prompting techniques have shown promise in enabling models to perform well on challenging tasks requiring intricate reasoning. Transferring reasoning capabilities from large to small models can reduce operational costs while maintaining task performance. We introduce an effective training approach involving pre-training and fine-tuning tasks on synthetic datasets using a multitask setup to enhance reasoning capabilities. By implementing our method, we achieve state-of-the-art performance on the ChartQA benchmark with Poly3, using significantly fewer parameters than previous methods. We conduct various ablation experiments to assess the impact of our techniques. The subsequent sections of this paper delve into related work, the construction of training datasets, our novel pre-training and fine-tuning methodology, the experimental setup, main results, conclusions, recommendations for future work, and limitations of our study. In the realm of vision language models, the combination of a vision backbone with a language backbone is common. Models like Poly3, which we build upon in this work, typically utilize a vision transformer coupled with a large language model. Existing approaches for chart understanding involve fine-tuned models like Poly3, Matcha, and UniChart, each with unique strategies to tackle visual question-answering tasks. While our focus is on refining self-contained models, we demonstrate that leveraging a larger LLM can further enhance performance. Section Summary. In this section, we explore the challenges of multimodal reasoning in visual language models, VLMs, that combine text and images, focusing on the difficulty of linking visual properties with textual content for complex reasoning tasks. We propose a method to enhance reasoning capabilities in VLMs by improving image representations and fine-tuning on synthetic datasets, achieving state-of-the-art performance on the ChartQA benchmark with a more efficient approach using multitask learning and significantly fewer parameters. Our work highlights the importance of pre-training tasks and fine-tuning strategies in improving reasoning abilities in VLMs, showcasing promising results for future research in this area. Section: The role of upstream OCR systems. In this section, we discuss the role of upstream OCR systems in processing charts. Charts can be challenging to decode into tabular data, so we can use OCR systems to extract text from chart images. By combining chart-specific logic with OCR, we can extract important information from charts, leading to improved quality downstream. In our work, we focus on using only the chart image for our model. To enhance chart reasoning, we utilize synthetic data during pre-training. Specializing the pre-training on chart-related tasks proves to be effective. We expand on tasks like chart derendering, which involves translating charts into code or tables. Our approach involves using programmatic templates to create complex question-answer pairs. Instead of using a large language model, LLM, to generate chart summaries, we use it to produce additional question-answer pairs with explanations. These examples, along with synthetic programmatic instances, play a crucial role in both pre-training and fine-tuning our model. ChartQA is a widely used benchmark for testing the reasoning abilities of visual language models, VLMs. It consists of a human-generated set and an augmented set, which is simpler and machine-generated. The dataset includes charts from various sources, with gold tables available for most sources. We also use a chart OCR model to infer tables for the Pew source, despite some errors in the inferred tables. In our work, we employ LLMs to generate additional examples with explanations using chain-of-thought prompting. We use the tabular data from the training set to compensate for the lack of visual input in LLMs. This synthesized data enriches the training set, especially with examples requiring extracting and reasoning with multiple quantities from charts. Our approach combines LLM for rationale generation and extra question-answer pairs, along with a programmatic method for generating arithmetic question-answer pairs. We enhance the training set by adding synthetic explanations for reaching answers. Using PlotQA, we predict rationales for input tuples of table, question, answer, with a 4-shot prompt. This set is referred to as ChartQA rationale S. By requesting justifications for correct answers, we reduce errors significantly, although incorrect answers may still occur, especially in the augmented set. To address the lack of diversity in the original training set, we generate additional examples using a 1-shot prompt. These examples cover identified errors from the model's performance on the validation set. We use PlotQA and PlotQL to create these examples, known as ChartQA Extra QARS-L. We lightly filter out examples that deviate from the intended structure but do not verify them for accuracy or fluency. For arithmetic questions, we create examples that require numeric reasoning or comparative analysis of chart elements. We use templates and predefined mathematical operations like median, max, and min. Each template includes a rationale to guide the model in solving arithmetic problems. These examples are based on the ChartQA human dataset and available tables. Section Summary. In this section, we combine chart-specific extraction logic with an OCR system to extract key information from charts, improving downstream quality as expected. We use synthetic data to enhance chart reasoning, focusing on generating additional QA pairs with rationales using LLMs and programmatic templates. By augmenting the training set with synthetic explanations and extra question-answer pairs, we aim to increase diversity and enable solving more complex QA questions in the ChartQA benchmark. Section: Resulting Dataset. In this section, we present the outcomes of our work on the resulting dataset. We have significantly increased the dataset size, which is around 20 times larger now. The details of this dataset can be found in the table, and more statistical information is provided in the section. Our sampling method involved using greedy decoding with a temperature parameter of 0. We utilized both augmented and human sets to create examples for our study. When comparing PlotQA and 2L, we found that using samples from both language models, LLMs, enhances performance. However, our ablation studies did not show a clear superiority of one over the other. We speculate that having diverse samples is more crucial than the size of the model, although we have not delved into exploring different sampling strategies. Our approach is based on the Poly-3 architecture and pre-training recipe, which includes two main components: a vision transformer VIT2B and a text encoder decoder UL2 to 3B. Initially, we followed the recipe outlined by the authors. The pre-training process involves training the vision encoder with a contrastive loss using the SIG-LIP loss and the language encoder-decoder with the UL2 loss. Both components are pre-trained simultaneously in a multimodal stage. Subsequently, we enhance the vision encoder to handle 812 by 812 resolution images and continue pre-training from this point. For the pre-training continuation, we incorporate a chart-to-table dataset mixture with the VIT backbone unfrozen to learn an internal representation of the chart. Although we do not explicitly use tabular conversion in later stages, this step aids in understanding the chart data. To learn this representation effectively, we combine various chart-to-table derendering tasks, including synthetic data, existing datasets, and data from challenges. The dataset sources, sampling weights, and the number of examples are detailed in the table. We maintain the existing table formats from the datasets and programmatically create tables for a small portion, ensuring normalization to a standard format. In the fine-tuning phase, we leverage synthetic data to refine the model for specific tasks. We explore two approaches for integrating rationales from the extended dataset. The first method involves changing the task target from answering questions to providing rationales alongside answers. The second method, inspired by previous work, establishes a multitask setup treating answer prediction and rationale prediction as independent tasks. The training loss is balanced between these tasks using a hyperparameter lambda. Our experiments encompass general learning hyperparameters for both pre-training and fine-tuning stages, followed by result interpretations. During pre-training, we continue training the Poly3 model with specific configurations on the Chart2 table data mixture. Subsequently, we freeze the VIT encoder and fine-tune the model on the synthetic ChartQA dataset with different settings. We validate the effectiveness of our techniques by evaluating the performance on the ChartQA test set. Our experiments demonstrate the impact of pre-training with the Chart2 table mixture on improving the model's ability to identify quantities in images accurately. The results, as shown in the table, confirm the significance of this pre-training step, especially as we scale up the dataset size, particularly in the augmented set. Section Summary. In this section, we present the results of our work where we generated a dataset that is 20 times larger, detailed in a table, and obtained using greedy decoding with a temperature of tau equals 0. We utilized both augmented and human sets to create examples, finding that using samples from both large language models, LLMs, improves performance without one being significantly better than the other. Our method builds upon the Poly3 architecture and pre-training recipe, incorporating a vision transformer VIT2B and text encoder-decoder UL2-3B, and we continue pre-training with a chart-to-table mixture to enhance the model's ability to work with charts. Section: Single task versus multitask. In this section, we examine the impact of using rationales in both single task and multitask setups in the ChartQA Rationale S dataset. When rationales were added in the single task setup, we did not see a significant performance difference compared to not using them. However, in the multitask setup, we observed an improvement in quality, especially in the more challenging human set. We labeled these setups as single-task rationale and multitask rationale in our analysis. We believe that the enhancement in performance is due to the better utilization of rationales, which help the model generate reasoning internally before providing the final answer. This improvement is achieved without the need to predict the rationale tokens. Next, we explored the transfer of reasoning abilities from POM2 to Poly3 using the ChartQA synth dataset. Through ablation experiments, we investigated the impact of extra questions, rationales, and pre-training stages. Our results showed a clear enhancement, indicating the importance of internal representation. Even without rationales but with the synthetically generated QA pairs, we observed an improvement over the original ChartQA performance. Furthermore, we found that the use of rationales continued to enhance quality for both single-task and multitask setups, especially in high data scenarios where the difference between the two setups was not significant. Based on our observations, multitask setup is preferred in practice due to its neutral impact at inference time and slightly improved performance on human-written queries in ChartQA. Our best performing fine-tuned setup is referred to as ChartPA-Li5B in our analysis. Additionally, we evaluated our method on FigureQA and PlotQA tasks to demonstrate its generalizability. We assessed performance in 3 operation regimes: zero-shot, quick adaptation, and convergence. ChartPA-Li5B outperformed Poly 3 across all regimes, showcasing significant improvements in chart understanding performance with just a few quick adaptation steps. We also identified areas for improvement by manually examining predictions on the ChartQA validation set. Despite enhancements, challenges remain in numerical reasoning, color reasoning, and complex reasoning tasks. We observed errors in computing mathematical expressions and working with colors due to the lack of color metadata in our synthetic data. Addressing these challenges could lead to further improvements in chart understanding and have broader applications beyond this specific domain. Section Summary. In this section, we explore the impact of single-task versus multitask setups in utilizing rationales in the ChartQA dataset. We find that while single-task setup with rationales does not significantly improve performance, multitask setup shows quality enhancement, especially in challenging scenarios. Additionally, our experiments demonstrate that the use of rationales consistently boosts performance in both single-task and multitask settings, with multitask being the preferred choice in practical applications, leading to improved chart understanding across various related tasks like FigureQA and PlotQA. Section: Task Leakage. In this section, we observed that when we train our model with different task prefixes, such as question or rationale, it may sometimes generate longer explanations resembling rationales instead of direct answers. Despite our model's improved ability to create numeric equations using chart values, it still makes errors in exact numeric computations because it treats numbers as tokens. To address this, we suggest using a program of thoughts (POT) approach instead of the chain of thoughts (COT) method to delegate arithmetic computations to a program interpreter. By fine-tuning our model with a simple prompt on the validation set, we can generate code for numeric computations present in rationales. We refine the generated rationales using a self-consistency approach, selecting the majority-voted answer from sampled rationales. Our method shows promising results, especially with self-consistency sampling. When comparing our results with prior work on the ChartQA benchmark, our model outperforms existing specialized models. Additionally, our approach can be combined with larger models through rationale generation, enabling more effective operation on text representations of charts based on questions. Looking ahead, we aim to address limitations such as the lack of color-related reasoning examples in our training mixtures and the need for more complex reasoning examples to further enhance the quality of our model.